Hi, this is part two of a two-part lesson on resistance, currents, and Ohm's law. On the last lesson, we focused on Ohm's law and the properties of voltage, current, and resistance, and looked at examples of how you can draw schematics of electric circuits and consider the small, but sometimes not insignificant, resistance that wires supply to electric circuits. In this lesson, we're going to focus on electric power and look at the difference between AC and DC currents and voltages. All of the images that you see in this video are attributed to OpenStax College Physics, published by openstax.org. It's distributed under the Creative Commons Attribution License version 4.0. Last semester, you learned that power is equal to the ratio of energy utilized or converted from one form to another in a given amount of time. And so let's see how this idea of power being energy per unit time, well, I already had it written there, transfers to electric circuits. And we start by remembering that voltage or electric potential is defined as the amount of energy per unit charge. Voltage is energy per unit charge, E over Q. Current is the amount of charge that flows past the cross-section of a wire or some other material per unit time. So if we multiply V and I together, we get energy per unit charge times charge per unit time. The Q's cancel, and we're left with energy per unit time, which is equal to power. So electric power can be calculated if you know the voltage and you know the current that that voltage produces. Power equals V times R, or sorry, V times I. Okay, well, consider this simple circuit consisting of a voltage supply, a battery, or some other voltage supply, which, when connected to a resistor, generates a current that flows through the resistor. Okay, so we can think about, okay, how much voltage is available to this resistor to utilize? Well, since it's the only component in this circuit, all the voltage is supplied to the resistor. And so we can calculate the amount of power that's being utilized by that resistor by multiplying the voltage that's supplied to it, which in this case is all the voltage, multiplied by the current that flows through it. P equals V times I. But we have an alternative approach as well, because remember Ohm's law? V equals I times R. So we can make a substitution. Instead of saying P equals V times I, we can say P equals I times R times I, which is equal to I squared times R. So you can calculate how much power a resistor uses if you know its resistance and you know the current that's flowing through it squared. Alternatively, V equals I times R, so I equals V divided by R. And you can plug that in here, in which case you get power equals V squared over R. So if you don't know how much current flows through a resistor, but you know how much voltage it utilizes, how much voltage it uses, square that voltage, divide by the resistance of the resistor, and that also tells you how much power that resistor uses. So in short, there's three different equations that you can use to calculate how much power a resistor uses. The one you use depends on the situation that you are studying and the things that you know. Now let's talk about the difference between direct current, or DC, and alternating current, or AC. And the first thing to realize is when we say direct current, we also mean direct voltage. Or alternating current, we also mean alternating voltage. So the word direct in this context essentially means constant. It means that there's some constant supply of voltage, and if the resistance situation is also constant, that means the resulting current is also constant. So if you plotted a DC current or voltage as a function of time, you just get a flat line like this. So alternating current means changing. And usually, when we say alternating current, we mean that the current and the voltage are oscillating between positive values and negative values. And pure alternating current is sinusoidal. Looks like a sine wave. And alternating voltage is sinusoidal as well. So we can mathematically write down expressions for alternating, for the value of an alternating current or an alternating voltage as a function of time. And it shouldn't be surprising that they look like sinusoidal functions. The voltage as a function of time equals some maximum amplitude, call it V naught, times the sine of 2 pi f, where f is the frequency of the signal and t is time. In the United States, the power that you get if you plug into a typical household receptacle is alternating current, where the frequency is equal to 60 hertz. Alternating current, you can write it out exactly in a very similar way. It equals some maximum current, I naught, times the sine of 2 pi f times t. Okay, let me introduce a new way of calculating or of quantifying an alternating current and alternating voltage, and it's referred to as the root mean squared, or RMS, voltage and current. And the reason we need to introduce this is because when you're dealing with an alternating current, and you say, well, what is the average value of that alternating current or that alternating voltage? You can't just simply find the average of that sinusoidal signal, because it spends just as much time in the positive as it does in the negative. So on average, the voltage is 0. On average, the current is 0. So you can't just talk about the average. So instead, what you do is you start by squaring the voltage as a function of time. So if you square something, and this is just qualitative, it's not quantitative, it gives you an idea of what the signal would look like if you squared it. It would look something like this. Whenever the value is positive, you square it, you get positive. Whenever the value is negative, you square it, you get positive. Okay, so now you do have a signal that has a non-zero average. It'll be somewhere in this regime. Okay, so that's the meaning of the root mean squared. So when we say VRMS, what we're saying is find the square root, that's the root part, of the average squared voltage. So you square the voltage signal as a function of time, you find the average of that squared voltage, and then you take the square root at the end. And that is not going to be 0. So it turns out that, we'll show how this is derived, but the root mean squared voltage of a sinusoidal function is equal to the maximum voltage, V naught, divided by the square root of 2. And the root mean squared current is the maximum current divided by the square root of 2. So in the United States, we say that household mains, the voltage that you get if you plug into a receptacle in your house, is nominally 120 volts. What we're really saying is it's 120 volts RMS, because it's an alternating voltage. So if you use this equation, you say, well, if it's 120 volts RMS, the actual maximum voltage is close to 170 volts. 170 divided by the square root of 2 is about 120. So in the US, if you hook up an oscilloscope to a receptacle in your house, you'll see the voltage oscillating between about positive 170 volts and negative 170 volts. And it has an RMS value of about 120 volts. Now, because of this oscillating nature of AC power, voltage and current spends just as much time positive as it does negative. So in your household wiring, the current is changing directions at a frequency of 60 hertz. 60 times a second, the current flips and changes direction. So let's think about how you figure out the power that can be delivered by an AC signal. Well, you start with the definition of what electric power is. Power is I times V. But now, if you're dealing with alternating currents, I is I naught sine 2 pi f times t, and V equals V naught sine 2 pi f times t. So if you multiply I naught sine 2 pi f times t times V naught sine 2 pi f times t, you end up with I naught V naught sine squared 2 pi f times t. Now there is something subtle about what we've done here, and that subtlety is that we're assuming that the voltage signal and the current signal are perfectly in phase with one another, meaning if you plotted current as a function of time and voltage as a function of time, the peaks and the valleys would line up with one another. That's not always the case, but let's assume that it's the case for right now. All right, so if you end up calculating the power of an AC signal by multiplying I times V, you end up with this thing that you need to evaluate in order to figure out what the average is, because what we find is the power is changing as a function of time, but we can think in terms of the average. Well, the average power that's delivered is not that hard to find, because what you do is you recognize that if you plot the square of the sine function, what you find is that the average of the squared sine function is equal to 1/2. So the average of this function, which is I naught V naught times the square of the sine function, is 1/2 I naught times V naught, or this. Now on the previous slide, we saw that there's a connection between I naught, the maximum current, V naught, the maximum voltage, and the corresponding RMS values, IRMS and VRMS. Or more specifically, I naught, the peak current, is equal to the square root of 2 times the root mean squared current, IRMS, and V naught is equal to root 2 VRMS. So we can plug these equations. We can plug root 2 IRMS in for I naught, and root 2 VRMS in for V naught, and when we simplify, we get 1/2 times root 2 times root 2. That all cancels and gives you 1, and you're left with the product of the RMS values. So one of the advantages of thinking about the RMS current and the RMS voltage is that the power, on average, delivered to an AC load, a resistor that's getting AC power, is equal to the RMS current times the RMS voltage. And this mirrors the power delivered by a DC current or voltage is equal to current times voltage. Okay. Let's end by thinking about a practical application. Let's say you have a long distance transmission line and you want to transmit electric power from one place, A, to some other place, B. And we know that, go away. We know that this wire, this transmission line, because it's made of a conductor, has a resistance, and that resistance is proportional to how thick the wire is, the cross-sectional area. The thicker the wire, the less the resistance. The longer the wire, the greater the resistance, and also the material it's made out of, the resistivity. Okay, we know that. So the wire has resistance, and the power that can be transmitted through this wire is V times I. Or if we look at it a different way, we can say that the power that's actually used up by the wire itself as the electricity is being transmitted from point A to point B is equal to substituting I times R for V. Another way to calculate power is I squared times R equals power. So we can think of, this equation right here tells us how much power is actually wasted by the fact that the the wire itself has electrical resistance. So in other words, this is sort of like a toaster effect. How does a toaster get hot? Well, you pass electric current through the wires in the toaster, and the resistance of the wires converts electrical energy into thermal energy. Okay, that's going to happen when you transmit power down a long transmission line as well. All right, so what this teaches us is that for a given wire, more power is going to be wasted if the current flowing through that wire is greater. So what this means is that if you want to transmit energy, and we use this equation as our guide, one way you can transmit or emit a given amount of energy is to use a large voltage and a small current. So for example, let's say you had 100 volts at 1 amp. That would be 100 watts. You can also transmit 100 watts if you transmit with a low voltage at a high current. So let's say 1 volt at 100 amps would equal 100 watts. Okay, but when it comes to how much energy is wasted in transmission, these two different scenarios have very different outcomes, because what we see is the amount of power that's wasted by the wire, dissipated by the wire, is proportional to the current, not the voltage. So that means if you want to transmit electricity long distances and you don't want to waste a lot of power, you want to do it in such a way that you have a high voltage and a low current, because the smaller current will result in less wasted power in transmission. All right, so that concludes this lesson. The next unit deals with electric circuits and studying electric circuits where you have more than one battery, potentially more than one battery, and more than one resistor.